Hello everyone, my name is Sahib and today we have four guests with us who will be explaining us few of the co-author papers in the domain of differential privacy. We have first Rakshit Naidu. He's an incoming master's in privacy engineering student at Carnegie Mellon University. He's currently working as a research intern at the University of California, San Diego, under Dr. Pentagao. His research interests hover around cryptography and machine learning in particular. Next, we have Aman Priyanshu. He's a student at MIT, Manipal, pursuing BTech in Information Technology. He's a technical head of Kryptonite and AI expertise subhead at Research Society Manipal. He's currently working on research in privacy-preserving machine learning and reinforcement learning. Then we have Archit. He is currently a CS undergrad at Punjab University, Chandigarh, and he's working as a researcher at OpenMind. His research interests are privacy-preserving machine learning, medical imaging, and natural language processing. And last but not the least, we have Priyam Basu. He's currently working as an NLP research intern at NTU Singapore and an NLP engineering intern at Tiger Singapore, where he's working on the R&D department. His interests majorly lie in the NLP domain, and he wants to pursue the field of healthcare industry. He has 3 research publications at conferences like ICML, Big MM, and proceedings in IEEE and Springer journals. He's also worked with Som Tiwari, a guest from last stream, and Rakshit, who's on the panel with us. With that, we'll begin. I'll hand it over to Priyam, and he'll explain us his first research paper, which is benchmarking differential privacy and federated learning for BERT models.
Yeah, hi Sahib. You've given me the control, right?
Yeah, give me 1 second. Yeah, you can go.
Yeah. Okay. Hey guys, I'm Priyam, and so today I'll be talking about this paper that I wrote along with Rakshit and a few other people. So the paper is titled "Benchmarking Differential Privacy and Federated Learning for BERT Models." So okay, so the way we started with this project was one day I just texted Rakshit out of the blue. He did not even know me, and I was like, "Hey, I would like to work on a project with you. Could you please give me some work?" So he was like, "Sure." And then I talked to him about how I'm interested in NLP, and he came up with this idea about how when so this paper, what it does is that we are trying to form an amalgamation. Rakshit's interest in research interest is in privacy preserving machine learning. That is, and right now he's majorly working in federated learning and differential privacy, and I was working in NLP. So this paper is an amalgamation of both of these concepts. So what we over here are trying to do is that we have tried to classify healthcare based data while at the same time also add a privacy feature to it. So, for example, if I'm suffering from depression, and then I want to talk to a therapist about it. Now, in fact, in current times or in current COVID times, we have seen that a lot of the things that we are doing now have become virtual. So you have virtual therapy sessions, for example, or for example, you even have therapists who you can talk to over text. So what happens is, suppose if I create a therapy app, for example, and I'm trying to talk to this app, it's maybe an AI, that's a therapy conversational bot. And so I'm trying to talk to him and I'm trying to tell the bot that I am depressed. But at the same time, I would not want for example, if the app is being made by an X organization, they will also have access to my data, and I would not want a third party to know about the fact that I am depressed. So that is what we have tried to. That was major motivation for us behind this paper. That how can we integrate such NLP concepts, such sentiment and analyzers or the chatbots, and how can we integrate a privacy feature to that so that the user information and the user data and especially the user identities can still remain private and no third party can have access to that. So that is what we have tried to do majorly over here. And so I'll just start off with the introduction. So we have tried to integrate differential privacy and federated learning with 4 major transformer models. Namely, they are Albert, Roberta, and Digital BERT. And I'll be discussing about them over the course of this paper, of this discussion, and Rakshit will continue from there on, explaining about the differential privacy and federated learning concepts. So, okay, I'll just, yeah. Okay. Yeah. So mental health, as everyone knows, is one of the most key and primary importance today. And a large amount of research right now is being done on trying to enhance medical support for it. Or for example, as I mentioned before, we have therapy chatbots, for example, where in case you can't talk to a physical person, you can talk to a therapy bot that can give you some sort of support, some sort of mental help, mental support, etc. So, depression is a very common mental disease, and a large amount of people suffer through it. So, as mentioned over here, in 2020, more than 264 million people were reported to be suffering from depression. And yes, and a large amount of these people, we live in a world today where social media is a very major part of most people's life, and people like to express their feelings, people like to talk about what how they are, how their mental status is. A lot of people do talk about that. A lot of people, and in general, the way people talk, you can somewhat infer that okay, this person might or might not be depressed, or may not be suffering from depression. And so a large amount of that kind of data is also available on Twitter, where people are speaking about the way they are feeling. So social media platforms like Twitter, for example, you have Facebook, Instagram, etc. Any social media app, they would have a lot of people speaking about these things. And these social media platforms basically let us observe these activities and thoughts and the feelings of the people. And that is and why we have tried to what we have tried to do over here is use data from Twitter, and accordingly we were trying to classify these particular tweets that we had scraped, as whether or not the speaker of that tweet, or the person who has posted that tweet, is suffering the depression or not. And as a benchmark, also we have also used another data set, which is prediction of which is for detection of sexual harassment. So I will also be going into the detail of how that data set was created. So, okay. Yeah. So, as mentioned over here, that the goal of the paper is basically to benchmark the effects of privacy measures like differential privacy and federated learning on BERT-based models, as mentioned before. And we have explored both the fields of IID and non-IID distributions, the details of which Rakshit will be getting into later this paper. Yeah. Okay. Yeah. So as you can see over here, this is the basic pipeline of our framework that we have created. So you have the raw user data, then which has been obtained from Twitter, etc. And this data is then pre-processed and tokenized. And this is basically a pre-processing step that we follow for the text. And once we have this processed user data, we are passing it to these four models. So the four versions of these models actually. So the first version is the baseline NLP model. The second version is the NLP model integrated with differential privacy. Third one is NLP model integrated with federated learning. And the fourth one is an integration of the NLP model with federated learning and differential privacy. So both the privacy features. Okay. Yeah. So a lot of work has already been done in the sentiment analysis part of it. So what sentiment analysis essentially is, that once you have any piece of, it could be any piece of any kind of language signal. So it could be maybe not even language. Actually, it could be the way it could be text, for example. It could be any kind of speech signal. It could even be an image, and based on an image, so example, if there's an image of a person and that person looks very sad, so the sentiment that we would get of that person from that image would be that the person is sad. So what sentiment analysis basically is a classification task of sorts, you could say, where unless we can also try to quantify the sentiment also, but at the same time, majorly, it is a classification task where we try to classify the person as the person through whatever form of input we have from that person, that is be it an image, speech signal, or an audio signal, or text signal. And we would like to predict that what kind of sentiment, that is a human emotion, is being conveyed by that person. And a lot of research has already been done for it. Like sentiment analysis right now is one of the most popular fields in NLP, especially right now. So like, and it has like major amount of applications. Like you could use sentiment analysis to get customer reviews, and you could find customer churn. You could get to, for example, if I have a large business, then I could get to, if I can analyze the sentiment of my customers, and I can know what kind of products they like, what kind of products are best pair with each other, and accordingly I can increase my business. So the applications of sentimental analysis are limitless in the current technical scenario that we have right now. So and a lot of work has been done in it. So we initially started out with with like elementary machine learning classifiers. We have KNN, logistic regression. You have decision trees, random forest, etc., which were initially used for the sentiment analysis task, which was essentially a text classification task. And yeah, and also, as I mentioned, at the same time, you can also try to quantify the amount of the sentiment. For example, if I want to classify a particular statement as whether or not it's a positive statement or negative statement, then I can also try to quantify how much of it is positive or how much of it is negative. So if I have a scale from 0 to 1, where 0 means negative and 1 means positive, then I can try to quantify the exact amount of the particular sentiment that is being conveyed by the particular input, from the particular input. Yeah. So initially we started off with machine learning classifiers, then we moved on to deep learning. There were, like, you could use neural networks were used, perceptrons. Then came LSTMs, which stands for long short-term memory, and it was basically an different implementation of RNN, you could say. And yeah, and then finally in 2018 came, so there was this paper called "All You Need Is Attention," and so that paper basically revealed to the world the concept of attention mechanism, which has laid the foundation for the transformer architecture. And this is considered to be one of the most revolutionary papers in the NLP industry, because ever since 2018, ever since that paper came out, all of the major amount of subsequent NLP work that has been done is being done in the research areas have been done in transformers only, because transformer architectures have proved to be much more superior than any other NLP architectures that are there currently. For example, be it an LSTM architecture or a BiLSTM, another simple RNN, or even a simple ML classifier. So that's why transformers are very popularly used. And the first transformer that actually came into play, the first most popular one, was BERT. The BERT stands for Bidirectional Encoder Representations Transformer. It was released by Google AI. And yes, that was considered to be a revolutionary. It was a revolutionary architecture. So yeah, so that was the part of it. So now I'll just move into. So I'll just give an explanation of the. I'll just give a visualization of the data that has been used, and after that I'll move on to the NLP architectures. Sahib, I can't open Chrome. Yeah, could you show the third last slide? Yeah. So this is the depression data set that we found. So this was an open sourced data set that we found off of GitHub, where there were 5 authors who had scraped Twitter for certain keywords. So there were keywords such as depressed, sad, not feeling good, etc. And they had scraped those tweets, scraped tweets having those particular key terms in them. And accordingly, then all the 5 authors went through all the tweets, and they were classified, and they were labeled by them. And this was a label data set, and yeah, it had around 3000 tweets finally. This is the initial, these are tweets that they had scraped themselves. So as you can see, it's not cleaned. So can you go to the second tab?
Yeah. Yeah.
Yeah, so as you can see over here, these are the clean tweets. So for example, in the data cleaning process, what we did, we removed all the hashtags, all the at the rates, any kind of special characters that we did not require. And also, okay, also we also removed the YouTube links that there was some extra. So a lot of the tweets on Twitter, they also have have a YouTube link attached to it. So we also removed those corresponding links. And this was the data that we had at the end. Although we did keep the emojis in this data, because we have in prior research we had found out that a lot of times the emoji that is being used by the user also pertains important information considering the context of that particular text. So yeah, so this was a binary classification data set, and with label 0 implying not depressed and label 1 implying depressed. And okay, could you go to the third tab? Yeah, could you scroll to the fourth page? I think the data set part. So this paper was actually it's a prior paper that I had worked on with Sohom and a couple of other authors. So the task over here for us was the text for was classification, or rather detection of cyber sexual harassment. So for this task of the paper, what we did was that we found, and there was no available data set, no open source data set online, because it's highly sensitive information. So what we did was that we found an open source data set which had a list of sexually harassing keywords. For example, any abusive keywords or profane keywords that are very popularly used in harassing statements. That's what was found from an online survey. So what we did was that we took that list, and that had about 408 keywords in them, but a lot of them were like unnecessary, very weird, and like they were futile. So we removed those, and the final list that we had about 93 keywords in them. So then we scraped Twitter for those 93 keywords, and after that we went through a manual data annotation process. So could you go lower? Sahil, could you scroll a bit? Yeah. So this was the original. Yeah. Yeah. Can you just show the table? Yeah. So
Actually, we have the
this
activity.
was the. Yeah, actually, I think there's some issue. I'm not being able to do the scrolling part on my end. Okay, yeah. So,
Try the keyboard.
yeah. Could you scroll to the table part, please? There's actually some issue on my end. Yeah. Yeah. So these are the tweets that we had at the end. So as you can see, so there are some keywords over here as mentioned. These were the keywords that were there from the list. Just a few samples, and this is a sample of those scraped tweets that we had got. So, for example, you can see that each of these tweets have at least one of those abusive or profane keywords in them, and they also have the at the rate tags or hashtags, etc. So after that, we had to go through the data cleaning process, where we again followed the same measures. We removed all the at the rates, we removed all the hashtags, the YouTube links, etc. But at the same time, we also kept the corresponding emojis that were probably used. Could you scroll down? Yeah, yeah. So just here. So these we followed a set of rules for the data annotation process. For example, text implying harassment with or without profanity would be labeled as 1. Text implying a threat, but in a non-sexually harassing way, is labeled as 0. But at the same time, if there is something that is implying threat and is in a sexually harassing way, then it is labeled as 1. So what we found was that a lot of the work that was already done in this field was to classify so there's this very popular data set called the toxic comment classification data set, which basically would try to differentiate any kind of toxic comments. And then there's a lot of work done on hate prediction, for example. But there was not a lot of work done that was specifically trying to target sexual harassment. And that's what we wanted to do over here. And so we tried to create a data set accordingly, such that such that a model, when trained on it, would be able to differentiate between a profane statement and a sexually harassing statement. Because if you're above the age of 18, then using profanity, even though morally wrong, is still not illegal. But then being sexually harassing, that is what is illegal. So that is what we were trying to target. And the final data table looked like this. So as you can see that all the at the rates, all the hashtags have been removed and they have accordingly been labeled. And all of them had followed these set of rules that have been mentioned. Yeah, Sai, could you go back to the paper now? Yeah, so both. So now I'll just move on to explaining the neural network architectures that we have used in our case. So yes, so the first, could you just scroll down a bit to both? Yeah. Yeah, okay. So BERT, as I mentioned before, one of the first most revolutionary transformer architectures that was released by Google AI in, I think, it was late 2018 or early 2019. I'm not sure about the exact date. So yeah, this was like, it's a heavily pre-trained model. So how BERT works is that BERT is okay. So BERT uses the concept of self-attention mechanism, and what it does is that instead of processing the entire input data as a sequence to capture the long-term dependencies, it basically takes it in the form of a matrix. For example, what we had seen before was, for example, with linear classifiers or with LSTMs, RNN, is that all of them used to take the input in the form of a sequence. But what BERT does is a bit different. BERT uses attention mechanism. So what attention does is that it takes two sentences and it turns them into a matrix where the words of one sentence would form the columns and the words of the other sentence would form the rows. And then it makes matches identifying the relevant context. So as a result of this particular matrix type input that is being taken by the model, it is very good because it is helping us to capture the long-term dependencies. That is the contextual meaning of, for example, if I have a very long sentence, and what happens is sometimes my first word may be related to my nth word also, and so that is the and it would be very relevant to the context in which the words have been used. And these are things that previously were not being picked up on very efficiently by LSTMs or RNNs. This is where BERT came into play, and BERT was outperformed any other classification architecture, any other NLP based architecture also for this particular task. So what BERT does is that it takes the words of the input sentence into subwords using the word space model, and then that these subwords are then fed into the model. So what it does is that it masks 15% of the input tokens for the model to detect the masked word. It also uses positional embeddings from the cosine and sine. So it has two blocks called the cosine and sine blocks in its architecture, which help us to get the positional embeddings also, so that we can replace the recurrence of the same words again and again. And a pre-trained BERT case, and yeah, so the input text is then passed through the BERT tokenizer, and for every individual tokenized input that you have that is fed into the BERT model, a CLS token, a CLS here stands for classification. So a CLS token is added at the very beginning of every sentence, because the training task here is a sentence classification, right? And since they need an input that can represent the meaning of this entire sentence, that is why this CLS token is put at the beginning of the sentence. And at the same time, another separator token, it's called SEP. So SEP stands for separator. So the separate token is added at the end of every text so that it can separate individual input for next sentence prediction. For example, so basically you have an input sentence. In the beginning, you have the CLS token, and in the end, you have the separate token. The CLS is for the classification part, that is to give a meaning to the entire sentence, and the separate token would be to separate it from the next sentence for the next sentence prediction task. And the final layer of both token, as you can see, is represented if it contains a token representation T and the classifier embedding would be C, then each T, that is each token, is used to predict whether the token is masked or not. So as you remember, I had mentioned that 15% of the input tokens are masked, right? So this is where it comes into play. that this classifier embedding is then used to predict whether or not each token T is each token T is masked or not, to predict if both the sentences are contiguous or not. And yeah, and then after that the text is then padded, and then padding is done on the tokenized text, and then it is passed into the classifier model. And BERT is also a heavily pre-trained model. So the pre-training of BERT largely follows existing literature on language model pre-training. Okay, so it uses the book's corpus, which has about 800 million words in it, and the English Wikipedia corpus, which has about 2,500 million words in it. So yes, and so this was the data that the BERT model was trained on. It is heavily pre-trained. So that is the end of, and yes, so this was the BERT architecture, and BERT after this, it led the way for many more architectures which were basically derived from BERT itself. And those are the models that we have used in this paper also. So the next paper that was the next model that was implemented was Robota. So Robota stands for a robot or robust BERT-based application. So basically, it was released by Facebook. I think the year following which BERT was released, and was released by Facebook AI. So it stands for, as I mentioned, stands for robustly optimized BERT training approach. So it is basically and it's basically an improvement on the BERT model itself. So at its core, it is a transformer that uses multi-headed attention mechanism, which enables it to capture the long-term dependencies. It essentially includes fine-tuning itself on the original BERT model, along with data and input manipulations, etc. And so what happens is that the tokens are sampled randomly in the input sentence, which are then replaced with the mask token. The mass language modeling, that is MLM objective, is basically a cross entropy loss on predicting the mass token. So over here, they use the mass language modeling concept for prediction of the mass tokens, and it uses the cross entropy. So originally, 15% of the tokens were selected, out of which 80% are replaced with the masked token. 10% are left unchanged, and 10% are replaced by any random selected vocabulary token. So by any random token basically. So after that, what happens is that in BERT, the authors had applied next sentence prediction, that is NSP, where the model is trained to predict whether the observed document segments come from the same distinct document or from a different one. So basically, what next sentence prediction is doing is that, as I mentioned before, BERT takes two sentence inputs at a time. So what next sentence prediction does is that it tries to relate between the two sentences and predict whether or not they are from the same input document or from a different input document. But what Robota does is that in Robota, and the NSP loss, that is the next sentence prediction loss, is removed, and thereby matching or even slightly improving the downstream task performance. And the model was trained with, I think, 125 steps with around 2000 sequences. And yeah, and I think there were, and also on 31,000 steps with 8,000 sequences of batch size, which basically improved the perplexity of the mass language modeling task that was used in BERT. And for tokenization, so the tokenization part in Robota is also different. So in tokenization, Robota uses a byte level pair encoding, which is basically BPE, and it is basically a hybrid between character level encoding and word level encoding, and it allows handling of very large vocabularies also. And so with a vocabulary of even 50,000 subword units, it would perform well. So I think BERT used about 30,000 vocabulary units, but this one Robota works on about 50,000. So yes, and yeah, so Robota was also heavily pre-trained, and it was pre-trained on much more data. So Robota uses about 160 GB for text pre-training, including 16 GB of books corpus and the English Wikipedia used in BERT. It also used the Common Crawl news dataset and web text corpus and stories from Common Crawl dataset. So the Common Crawl dataset is very popularly used even for pre-training and even for benchmarking purposes in case of question and answering systems. So yes, so that is it for Robota. Next, we move on to digital BERT. So, Sahil, could you? Yeah, thanks. So yeah, so digital BERT was basically again another version of BERT, and it majorly uses the concept of knowledge distillation. So what the knowledge distillation basically is that, so you have very, so you, as I've mentioned, so these models, that is BERT, they have like millions and millions of parameters. So these models are essentially very large in size. Now, so when your models are being large in size, at the same time, it's also very difficult to scale them, because your, first of all, the computation cost will be much more. The amount of time to train it will be much more, and at the same time, the pre-trained weights also you get from there will also be a lot. So what knowledge distribution concept basically follows is that it trains a small neural network in the same way a large neural network is trained. For example, you have a large neural network like BERT. So what digital BERT basically is, it is just a smaller network, and it is following the same training procedure as BERT was trained. Even though the parameters of it were only 97% perform. So what happens? So what? No, sorry, not 97%. The parameters of digital BERT are basically half of the parameters of BERT, but it still retains 97% of the performance from there, and it does not have any token type embeddings or tooler. And yeah, as mentioned, only half of the layers are retained. And yeah, as it uses knowledge distillation, and yeah, okay. So it also follows the concept that once a large neural network has been trained, its full output distributions can be approximated using a smaller neural network. This in some sense is similar to posterior approximation, the details of which I will not get into now, because posterior approximation and callback divergence is something that is just it's a different discussion in itself. But yes, so basically the essence of digital BERT is that it is using a smaller network with half the parameters of BERT, but it is following the same training procedure. Yes, that is, yeah. In supervised learning, a classification model. So if you want to know more about knowledge distillation, I could try, if I wanted to summarize it, I could say that in supervised learning, that a classification model is generally trained to predict an instance of a class by trying to maximize the estimated probability of the labels. The standard training objective thus involves minimizing the cross entropy between the model's predicted distribution and the one-hot distribution of the training labels. A model performing well on the training set will have to predict the output distribution with a higher probability on the correct class and the near zero probabilities of the other classes. But some of these near zero probabilities that I mentioned before of the other classes are larger than the others, and therefore reflect in part so basically the generalization capabilities of the model and how well it could perform on the test set. So yes, that is it for knowledge distillation. And the final model is the Albert model that we had implemented. So yeah, so Albert stands for a light BERT semi-supervised learning for language representations. So this paper was written as a troll on the BERT paper. Like if you will go into if you ever read the Albert paper, and then you will just keep on laughing, because they raise a lot of shots on the on Google A and the BERT paper. So what it basically does is that it uses factorized embedding parameterization, where the size of your hidden layers, where the size of your hidden layers from the vocabulary embeddings that you have, they are isolated by projecting one hot vectors into lower dimensional embedding space. And therefore it makes it easier to increase the hidden layer size also, without having to significantly increase the parameter size of the vocabulary embeddings. And even cross-layer parameter sharing is also used at the same time. And the cross-layer parameter sharing, in an essence, helps us to increase, you could say, the depth of the depth of the network. Yes, so that's why the cross-layer parameter sharing is also very useful. And a large Albert, as mentioned, a large Albert model has about 18 times fewer parameters. That is, if BERT has 100 parameters, then it has like 1/18th of that. So that's how smaller Albert was. And it also uses sentence order prediction loss. It's a loss function that it uses to model the inter-sentence coherence, which also enables the new model to perform more robustly in multi-sentence encoding tasks. So for example, in BERT, we had yesterday take two inputs at once, right? So over here, I can give multiple inputs also, but since in this case, it's not using NSP, it is using SOP, that is sentence order prediction. So I can even give multiple sentences as input to the corresponding algorithm input, corresponding algorithm model, and it would classify very well accordingly. So yes, and it also performed very well on the benchmark tasks. And Albert is actually a BERT model that is quite popularly used for deployment purposes. Also, any kind of task where I would have to. So, most industries right now in the NLP domain do not like to go forward with transformers because they are very difficult to they are very difficult to deploy, as they are heavily pre-trained and their weights are very the heavily pre-trained weights are very difficult to scale on a larger system. So that's why Albert was something that came into play, which was using only 1/18th of the parameters. And it was created as a much more scalable version of BERT also, even though it did not perform as well as BERT. Like the BERT is a BERT and Roberta results are much better. But at the same time, it is much better if you're looking to deploy a particular BERT-based software. So yes, so that brings us brings us to the end of the NLP part of the paper. Following is the differential privacy and federated learning part, which Rakshit will continue.
Thank you, Priyam. Okay, so let me go into the details of differential privacy and the federated learning part of this paper. So first, let me talk about differential privacy. And out here, just 1 second. Yeah, the definition that you can see out here, this is the formula for differential privacy, where M and S denote some random mechanism, and also S is an output. And D and D dash are two different data sets, where D dash is just one individual record away from D. So what happens is that if D has n records, D dash has n minus 1 records, right? And you have two parameters called epsilon and delta, and these are the ones that actually talk about the privacy within differential privacy. So epsilon represents the privacy budget, while delta talks about the probability of how much you can accidentally leak information. So delta is usually put as 0, and when you put it as 0, people actually call it as call your system as epsilon differentially private, or sometimes even delta is put as 1 by the length of the data set, because the size of the data set actually matters when you talk about the probability of the information that leaks from your data set. So usually they put it to the orders of 10 power minus 4 or minus 5. So let me talk about DP-SGD, that is differentially private stochastic gradient descent. Sahil, could you show the other paper?
The deep learning.
Yeah.
Can let go of the mouse.
Okay. Yeah, thank you, Sahil. Yeah, so this is the deep learning with differential privacy paper by Google AI, and this was presented at ACM CCS 2016, and they came up with two additional information within the stochastic gradient descent algorithm. And the first addition was that after computing the gradient, they actually clipped the gradient to a certain factor, and they called this as the gradient norm bound, which is called C, and we usually call it as the gradient clipping factor. And the second addition was the addition of noise. So they added noise within the training process in order to make your gradients more garbled, and also it enhances privacy as such. So what they found out was that when they used this differentially private SGD, it actually preserves privacy, and on top of that, you can actually generalize information over your data set, and you don't need the original gradients in order to learn something. Even if you have something which is noisy, you can still get a really good result after adding noise. Yeah, that's what they said essentially. So let me talk about the federated learning part now. Yeah, so this was the paper by Google AI again, called Communication Efficient Learning of Deep Networks from Decentralized Data. This was presented at AI Stats, if I'm not wrong. And yeah, let me just show you the algorithm of federated learning. So what happens in conventional machine learning is that you usually send your data to the cloud or to your server, and you have a machine learning model that trains over that particular server, and only the results are sent back to your local client, to the local client device, right? But in what federated learning does is that instead of sending your sensitive information, that is your sensitive data, to your server, you only send your model updates to your server, your local model updates. So now out here, you have two things, that is a global model and a local model. So the global model actually learns from all of these aggregated information from these local models. So the local models are just copies of the global model. And what happens locally is that you train your model on the client's device itself, and only the model updates are sent back to the server. And this model updates are then they come up with something called federated averaging. So basically, with these model updates, that is the new model parameters after each round, you average them, and this averaged new parameters become the parameters of the global model for that round, and then you continue again and again for some particular global rounds. So out here, instead of sending your sensitive data to the cloud, you're just sending your model updates to the cloud, so that, and this enhances privacy a lot, because you're not sending any sensitive information from the clients itself. Yeah. And out here you can see this is the formula, and that is the algorithm, and the server actually chooses some particular clients in that particular round. So the capital C denotes the subset of clients that they choose, while K denotes the total number of clients in that round. And also, and then they perform the client update, which is the update of the global update of the model parameters from the clients itself to the global model. Yeah, and here you can see the averaging step that takes place on the server, which refers to the federated averaging algorithm. While in the client update, this is the normal stochastic gradient descent that runs within the device itself, that is the local device, and only the new weights are sent back to the server. Yeah. And in our paper, we actually use some kind of local DP within federated learning. So what we do is that we add differential privacy only to the client update function, so that when you actually send the new weights, these new weights are actually tainted with differential privacy. So these are actually, so in the last slide that I'd shown, you actually add noise to those parameters, right? So this is actually done to the client update weights, and the new weights with differential privacy are sent back to the server, and then these are then averaged out for that particular round. Yeah. So coming back to our paper, yeah. So let me talk about the experiment side. So out here,
can you give me access to the mouse?
Okay. Yeah. So we used those two data sets that Priyam explained, and we also used Opacus, that is a library for differential privacy by Facebook AI, and we actually implemented DP-FL and also DP+FL, that is the local DP+FL, on top of those 4 networks that were discussed by Priyam. And we use these different epsilon values, that is 0.5, 5, and 15. And when you say you have epsilon is equal to infinity, you're trying to say that your model has no noise. So basically, it's just a normal model, like a normal machine learning model. So an epsilon is equal to infinity actually means no noise, while an epsilon is equal to 0 means infinite noise, which does not really exist. Yeah. So we actually benchmarked it on those 2 data sets, and here are some results. Yeah. And with centralized DP, and we tried working on it with FL IID and non-IID. So what IID actually stands for is identical and independently distributed data. So what happens is that since we are running it on a simulated platform for federated learning, we are just running it on collab notebooks, and you're not actually implementing federated learning as such. So there's something called IID and non-IID. So in IID, what we assume is that each and every client has identical and independently distributed data. So they have the equal number of samples of the same particular training examples or the test examples that they have. So every client has the same number of training or test examples in IID. While in non-IID, you say that it's non-identical and independently distributed, which means that some client might have low amount of training examples or test examples, while another might have more. So in practical scenarios, what happens is that non-IID is very common because maybe some person might be using their local device, that like a mobile phone, a lot, while someone might not, right? So it might differ from person to person. So non-IID actually gives you a really good sense of what data is in a practical scenario. Yeah. So these are the average test accuracies that we got over both these data sets. And overall, what we observed is that the huge models, that is the Roberta and also the Roberta and BERT, actually don't degrade gracefully than the smaller models like Albert and Distilbert. So because Albert and Distilberts are really small, and what happens is that when you add noise, they tend to show more disparate impact. What I'm trying to say is that your accuracies would change a lot with the different levels of epsilon that you choose, right? So yeah. And the second thing that we observed was that in the non-IID setup, which is the more realistic scenarios in medical applications, the utility degradation is actually higher than IID setup. So what happens is that the standard deviation actually for lower epsilons is actually way higher than the higher epsilons. And this is actually quite intuitive because when you're running it on a non-IID setup, your data is not distributed identically, and this is why you see more degradation than in the IID setup. And the third thing that we observed was that since the training data set was very small, we just one second. So yeah, DP's effect on utility is more detrimental than when more data is provided. So this basically means that because we use small data sets, DP's effect was higher because you're trying to add noise, and when you use a smaller data set, when you're trying to use a larger data set and add noise, you don't observe much change, right? Because it's already pretty huge, and yeah, even if you add noise, it doesn't actually matter towards the end result. While when you look at small data sets, you get a much more harmful impact. Yeah, and these are actually shown by those papers by Florian Chamer and Dan Bonnet at ICLR 21. Yeah. So this brings us to the end of this paper. Yeah, if there are any questions or anything of that sort? Otherwise, we can go to the
How exactly does epsilon and delta affect the privacy? I didn't quite get that part.
So yeah, so can we show the other paper, the DP-SGD one? Yeah. So out here, there were these two additions that were done. That is the clipping of the gradient and adding of noise, right? And actually, if you see these parameters, that is adding the noise, you actually use when you use a Gaussian distribution of mean is equal to 0 and you have a sigma. So out here on the right hand side, you can see these moments of accounting subheading, right? Can actually sigma, when you choose it to be the root of 2 log 1.25 divided by delta divided by epsilon, that actually tells us how epsilon and delta are related, because you have to choose your epsilon and data based on what you have. As in, a delta is usually put as 10 to the power of -4 or -5, while if you want an epsilon of 0.5 or something, or 5 or something, so you basically put these and you plug these two parameters to find that particular sigma, and then based on the sigma, you can add the particular, you can draw random samples from that particular distribution, Gaussian distribution of that particular sigma, and yeah, and then using that noisy samples that you get, you can add it to the gradients, and this is how you get differentially private SGD as such. Does that answer your question?
Yeah, it does. And another thing is that when you said that if delta is closer to 0, then there is a higher chance of information leak, right?
Yeah, what I'm trying to say is that delta is equal to 0 actually gives epsilon differential privacy, because you don't have delta at all in that equation, right? Can you go back to that equation as such on our paper? Yeah, can we go to the second page? I'm sorry, the third, I think. Fourth. Yeah, this one. Yeah. So out here, when you say delta is equal to 0, you have only the probability, this thing less than e to the power of epsilon into the probability of the other data set d dash, right? And when I'm trying to say delta is equal to 0, you have an epsilon differentially private mechanism as such. And actually delta refers to the probability of accidentally leaking information from your data set. And this is usually don't think about this. And in practice, we usually put it as 0 or something like 1 by the length of the data set. So it's pretty small. And yeah, it's not actually used as such in like for simulations and all. But yeah, you just get an epsilon differentially private mechanism when you put delta is equal to 0. Yeah. Does that answer your question?
Yeah.
I think you can read more about it out here. Yeah, talk about what delta is. And when you have delta greater than 0, it's called approximate differential privacy, right? Because you don't have epsilon differential privacy. Okay. Should we go to the other paper?
Let me check. We'll be doing party, right?
Yep. Okay. So this is a paper called DP-SGD versus PATE, which has less disparate impact on model accuracy. And this was with Archit, who's also on this call. And here we actually look at the fairness aspects of DP-SGD, and we also compare it to another DP mechanism, which is called PATE. So since I've explained what DP-SGD is, I think we can go ahead and explain what PATE is. Archit, do you want to do that?
Sure. Am I audible?
Yeah.
Yep.
Yeah. Get the access.
Rakshit, you have the control now.
Wait. I'm not able to access.
Yeah, you're able to move.
Okay, I'm not able to. Okay, so as we are talking about differential privacy, so we have talked about DP-SGD, and as we know, like DP-SGD is performing gradient clipping and like basically adding noise to the algorithm and then performing the descent. So what happens is sometimes when we are talking about DP-SGD, the sensitive data or the sensitive data can be leaked to the public while clipping those gradients. So that causes a disparate impact. And also the motivation behind this paper was that when we are training a model, if there is like an underrepresentation of a certain class or label, that causes the model to like train it on the other model or the classes and cause that underrepresentation of that particular class. So that's a major issue in machine learning. And since we are also fixated on privacy, but we are not considering fairness as a part. So I think fairness and privacy goes hand in hand. So this idea came into being, and we looked into another mechanism of data privacy that was published by Google AI. That is private aggregation of teacher symbols, that is PATE. And can you show that paper? Sahib?
Yeah.
PATE. Yeah, this one.
Yep.
Okay, so this is the basic architecture of PATE. What they said was like, if we train our models in such a way that the access to the original data is like completely cut off, and we are just giving access to the data that is produced from the original data. So that is something that can preserve this privacy and also guarantee a certain level of fairness. In PATE, what we do is like we have certain data set, and we split it into n disjoint data set and then train n teachers on it. And based on it, we get a word count. Like, for example, if we are training it on MNIST, so we have 0 to 9 classes. And if we are getting, let's say we are predicting 9th class and each teacher is giving certain label to it. So in the end, we are getting a word count on what each class is getting from each teacher, somewhat like that. So in the end, we are getting a word count that is totally different from the original label that is. That way, we guarantee a certain level of privacy. But the main idea behind it is like if it came from the idea of a teacher teaching a student. If we have like n teachers, they are teaching some subject to some like junior teacher, and that teacher is then teaching the students. So what it'll do is it will just taking the junior teacher would take in all the crucial points and then teach those points to the student. That was the basic idea behind PATE. That's what the model is doing. As you can see, it's taking sensitive data and dividing into n data sets, and then training n teachers on it, and then getting a vote count and getting an aggregate model on it. And then in the end, to like get a better privacy guarantee, we are adding noise to the next data that will be training on the student, right? For example, as we know that MNIST has 6,000 images. So if you are splitting it into n classes, so I think it will have like 1 by 10 is 60. So 60 images, 600 to 60 images would be there in each data set. So 600, that would be 10 in this joint subset. We are teaching for 10 teachers, and then we are getting a vote count for it. That was PATE is. Then secondly, what we can we go to the original paper that we published?
Yeah.
Okay, so I've explained what PATE is. Now I'll be explaining what the experiments we performed on PATE. As we know, like I have told you guys, that DP-SGD has a disparate impact on the underrepresented groups. So what we did was, like, we took the two data sets that I mentioned for MNIST and SOTA, and we imbalanced them. And for example, if in MNIST, as you can see, we imbalanced the class 8. Class 8 to have a sample of only 500 samples. By 500 samples, I mean there was a 1:10 imbalance. That means for the 10 classes there are, so there for every one image in class 8, there are 10 images in the other classes. And in SVHN, we performed a 50% imbalance because SVHN is quite imbalanced to start with. So we had to like bring the images down to first to 5,000, then perform a 50% imbalance to make the data set average like more balanced to perform these experiments. Then furthermore, moving on, scroll down. Okay, got it. Okay, so next is the experiment we performed. This is the we performed this experiment like we trained this DP-SGD algorithm and the PATE algorithm on MNIST dataset, and we ran this experiments for 5 iterations and then got an average out of it and got the standard deviation for each class that we have. So as you can see that DP-SGD is performing way worse than PATE in terms of accuracy as well as fairness. By fairness, I mean the standard deviation is quite large for class 8 in DP-SGD than for in PATE. That clearly shows that PATE is able to like more fairly determine an outcome than DP-SGD. Then secondly, we moved on to the SVHN dataset, and there we saw that DP-SGD was performing good in terms of accuracy, but in terms of fairness, it was still performing way worse than PATE. As you can see, the standard deviation is very less in PATE than in DP-SGD. So that means that these two experiments like clearly showed us that PATE was way more fair than DP-SGD. This was the outcome that we were looking for when you have the idea that we should compare these algorithms. And then furthermore, we tried to explore the field where how PATE is being more fair. And then we thought that since PATE is having access to the public data, that is the teachers in PATE are actually having access to the public data and performing the major task of getting that privacy guarantee. So let's explore how the number of teachers affect the performance of PATE. So this was an evaluation study that we did. And as you can see, for one teacher, we had lower accuracy. That's because like one teacher won't be able to give us that vote count. So because we are sending all the data set to one teacher and then getting a result out of it. And that means that we are just getting the results directly out of one model. So as we moved on, like for 10 teachers, 10 was the optimum teacher count that we had, which gave us the best result. And that's because like we were able to fairly distribute our whole data set into like 10 disjoint data sets, and that was able to give us a better vote count for the aggregate teacher, which further led us to give us better data set to train the student. Then as we see that from 10 to 50, we was able to see a stagnant growth, like the accuracy wasn't fluctuating that much. And there wasn't major change that was coming around. But as we reached 50 and moved forward from that, we saw that the accuracy started to decrease. And that was because as we move forward from 50, the data set becomes too small to be distributed among 50 or more teachers. And that caused it to like train very inefficiently and give us a very worse vote count. And that wasn't optimum to get that fairness or the privacy guarantee that we wanted. So in the end, the conclusion we derived were that as we know, DP-SGD has a disparate impact, but PATE doesn't show that much of a disparate impact. That is, poor gets poor. So it was a good thing that we were able to prove that PATE is the go-to algorithm to get the fairness guarantee that we want. But there was another thing that we looked into, that the PATE was training our teachers on public data. If we don't have access to that public data, we won't be able to use this algorithm. So that's one limitation that we have, that if you want to use PATE, you must have some public data in the teacher, else it won't be the go-to algorithm. And secondly, we have to determine a optimum number of teachers to get the best fairness or the privacy guarantee that we want. And that was the result that we got. And since in this case, like this was trained on a smaller model, for MNIST we use only a 7 to 8 layer architecture. So 10 was the optimum count that we got there. But for SPHN or resident rating, there may be some changes that may be required. So yeah, these were the outcomes that we got from this paper. Yeah, any question?
I think one thing we failed to mention was that with PATE, that is the application study, when you increase the number of teachers, the thing is that it drops after you increase it to somewhere around 50 and 100 teachers, the accuracy.
Yeah, while I told, I guess, right, that for a certain level it becomes stagnant and it starts dropping. Yeah, I think you didn't say why though. Why that happens? Because the data set isn't like big enough to be divided into the close number of teachers. Right. Yeah. That I think that is the reason. Only when you have a higher number of teachers, but when you have lower number of teachers, it's because you don't learn too much because you have very less number of teachers. Yeah. Any question?
I guess we can move on to the next one.
Cool. Thank you, Archit.
Thank you, Archit.
Thank you, Sahib. Yeah, so this is the last paper that we'll be talking about. That is where we try to integrate differential privacy and interpretability. And the idea about this paper is that when you add privacy aspects to your machine learning model, it obviously you get reduced accuracy on your model. But this also comes at the expense of model interpretability and explainability. The thing is that because you get a very low accuracy, I mean lesser than when you have the conventionally trained model, your model wouldn't be interpretable enough for, let's say a random user who wants to look at the results of your model. And this is really important when you talk about medical scenarios, because maybe a doctor would be using your model, and let's say you're trying to use differential privacy because you have certain doctor-patient confidentiality, or maybe there are certain privacy laws like HIPAA, that is the Health Information Portability and Accountability Act. And so basically what happens is that you're trying to use differential privacy over your, let's say, diabetic retinopathy model. And so yeah, you want your model result also to be very explainable to the doctor and also interpretable, so that he understands, okay, so this is where something is going wrong, and so that he can identify certain features from the result and make decisions related to that. So this is the motivation behind this paper. And in this paper we talk about two different DP mechanisms. I mean, DP actually refers to the addition of noise, and we out here, we talk about local DP and global DP. And what we mean by local DP is that we add noise to directly to the training samples, that is straight to the images itself, and then train the model over those noisy images, right? And this is called local DP because you're doing it locally on your training data. While global DP actually talks about the normal DP-SGD, where you're trying to have, train your model on like normal images, and your training mechanism uses DP-SGD, and and then you get your results. So these are the two different mechanisms that we've looked into. And there's another mechanism called output DP where you can actually add noise to your output itself, but that actually wouldn't be very plausible in a medical scenario because you don't want your output to be very noisy as such. Yeah. Or else the doctor might make wrong decisions. Yeah. Let's go to the related work, if possible. Yeah. Just 1 second. Okay. Yeah. Yeah, this is the image that I want to talk about. That is how we went about it. So here we added local DP, that is noise, straight to the patient data, and then we trained a model over it, and then we interpreted it. While the second one is the global differential privacy with DP-SGD, where we trained a model with DP-SGD on the patient data, and we had a trained model by the end of it, and we interpreted it. So these are the two application schemes that we use. And since I've talked about different DP-SGD, so I won't go much into that. So I'll talk about the GradCam, that is the interpretability method that is normally used for classification tasks. So CAM actually refers to class activation mapping, and these are actually a linear combination of the weights that you get from the last layer, that is the global average pooling layer or the gap layer, to the and the activation maps that you get. So out here you can see that you take a ReLU of both of these. It's a linear combination of both the weights as well as the activation maps A, right? And we take a ReLU because we only want the positive activations, and while the negative ones are straight, they're sent and they're made to 0. Yeah. And yeah, so over the evaluations part, we actually looked into 2 data sets. Actually, Aman would talk about this because he was working on this project, and all thanks to him because yeah, he ran some of the experiments.
I mean, thanks a lot. We worked on 2 data sets essentially. The Aptos data set, which is the retinotherapy data set for prediction of blindness, and the cats versus dogs data set was for simple classification model between cats and dogs. Basically, the medical side of our classification task was shown through the Aptos dataset. We go through each experiment with a batch size of 32, and we iterate over different epsilon values to compare our results and and basically showcase how differential privacy and interpretability are linked, how different epsilon values will affect different different points of interpretability. So as you can see, we take over different epsilon values. One case, as Rakshit told, the local differential privacy method, wherein we took epsilon values 0.5, 0.25, 0.5, and 1, and the other one, which is the DP-SGD, where we took epsilon values between 1 and 5, over 1 and 5. So you can see that we took different kinds of parameters, metrics. The first one being the average drop percentage, wherein the average drop percentage, wherein the maximum positive difference in the prediction made by the prediction model using the input image and the prediction using the saliency map is verified. The ideal case for the average, the ideal case for an average drop would be very low. That is, if the model was perfectly functioning, then it would have a really low average drop value. Whereas then we come to the increase in confidence percentage, which is the average. Basically, the aim here is that how confidently the model is able to predict a certain claim or a certain prediction. Here we are looking to improve this. That is, the higher it is, the better it will be. And yep. If you can scroll down, we have different. Yeah, we have a comparison between different epsilon values and the different metrics. Here we can see that, like as we discussed, average drop, the metric decreases as epsilon increases. So as previously discussed, as we increase the epsilon value, our privacy leakage also increases. That is, the data becomes more and more normalized to the original input values. Therefore, we can see a consistent decrease in it. Similarly, for average increase, we can see an increase as the leakage increases. And therefore, by the end of it, we have 95%. Same with average normalized input scores. The first table was with respect to the VGG16 neural network, and on the cats and dogs dataset with Gaussian noise. So there are two different types of noise we take a look at in these particular experiments. The Gaussian noise, which is based on the bell curve or the normal curve, and the Laplacian noise, which is based on the doubly exponential noise curve. So the Laplacian noise distribution or the Laplacian noise function is more closely related to the pure differential privacy equations of the of the DP-SGD, whereas Gaussian noise provides us an approximate value for it. If we go down further, I think I want to show the image first. So here we can see on the Aptos dataset, that is the blindness detection dataset. The first image represents the epsilon value 0.25. So the first image represents the original picture itself. After that, 0.25, 0.5, and 1. As we can see in the original, as the epsilon is increasing, the point of interest or the region of interest the GradCam is displaying or focusing on reduces, and we can see that it is mostly focusing towards the point of highlight, which is the error or the reason due to which the blindness is occurring. We can see decreasing area, and the point of the region of interest gets more and more focused as epsilon increases, again due to consistent increase in privacy leakage. These two were the Aptos dataset was run across two different neural networks, the ResNet network and the AlexNet network. The ResNet 18 network, I believe the ResNet and the AlexNet both are pretty baseline models for computer vision classification. The AlexNet being the smaller one, and we are able to display both of them side by side as a comparison that our approach or the interpretability plus differential privacy can be baselined, and it works across different models as well. Then we these graphs, again, epsilon values with respect to average drop percentage, average increase percentage, they both again show the previously stated results. Although there were disparities, it is closely linked in a general way. I think if you can scroll down further, there is then we also, as we discussed about the two different kinds of noises, the Gaussian noise and the Laplacian noise, we display results from both of them. As you can see, the region of interest, particularly in the dog images, as epsilon is continuously increasing, that is privacy leakage also increases. The image gets more and more focused towards the animal's head. For example, taking in Laplacian DP-SGD image for the dog first, we can see in the first leftmost image is the original image. Just after that, the point with the lowest epsilon value, that is 0.5, we can see the region of interest is quite distributed compared to as epsilon increases, we have a bit more focus on the head of the dog. And as we continue to increase it, the focus continuously increases on that particular animal. Similarly for Gaussian DP-SGD as well, as it is an approximate of the Laplacian noises only. Comparison between, one second. Yeah, comparison between ResNet 18 and AlexNet, the different test accuracies for the Aptos DP-SGD, Aptos dataset. We can see that ResNet almost consistently was better than AlexNet, except epsilon is equal to infinite. That is more or less due to the fact that ResNet, I believe, being a larger network, has a tendency to overfit, and all the differential privacy was since it adds noise, it has a factor to fix generalization. However, it cannot be that it cannot fix as well. And I believe we discussed PATE, which has a better chance of doing the same. So, yep. In conclusion, I believe that both differential privacy or privacy related, privacy preserving machine learning and interpretability have a can be combined or integrated with themselves, and they both provide great opportunities in fields like medical data, law related stuff, etc., where although we do not have the legal rights to the data, or we do not have full access to the data, using PPML, that is privacy preserving machine learning, we can get access or train our models on it. Whereas using interpretability or explainability, we have a chance to explain what the neural network thinks or is predicting to people who are not from the AI or the DS data science environment.
Thank you, Aman. If you have any questions on the panel, then we can take it. That's all, right?
Yeah.
Yep, that's it. I think one thing that I forgot to mention was that it's been shown that when you use a Laplacian distribution with the parameter of 1 by epsilon, it's supposed to satisfy your epsilon differential privacy constraint. So this is a really cool result, because the thing is that when you use Gaussian noise, it doesn't actually satisfy epsilon differential privacy. It just approximates it towards your epsilon differential privacy. It never actually reaches that point. While when you use something like Laplacian, you actually get epsilon differential privacy with the parameter of 1 by, when you use a parameter of 1 by epsilon. And based on that, you can say that Laplacian is kind of something like a pure DP, and while Gaussian has something like approximate DP.
Yep. That's very interesting. If you have any doubts from the panel, we'll take it up. Also, for the interpretability part of it, how did we how do we compare how good our model is performing during interpretability? And like generating CAM maps, what is the metric that we trained it against?
Actually, we used those two metrics that were displayed in the GradCam++ paper. That is the average drop and the average increase in confidence. While there are other metrics like localization evaluations That is when you try to use something like a pointing game metric, that is at each and every pixel, you try to see whether it's a hit or miss, and then you divide it by the total number of pixels in that particular region of interest. So yeah, you can use that metric as well when you talk about localization evaluations. But right now we wanted to go with faithfulness evaluations because we did not have bounding box over the images. So the thing is that when you talk about localization evaluations, you probably need a region of interest using those bounding boxes, and then you try to find out how much energy or how much how much highlighted portion is there within that bounding box itself, right? And yeah, it's hard to find data sets that have this feature. So because you probably have to annotate it manually, otherwise, yeah. And
yeah. Also,
other
I
metrics.
think, yeah, go ahead.
Sorry, there's another metric called human trust evaluations. That is where you actually send these images straight to like random human subjects who do not have any deep learning experience. So what they can do is that they try to vote, saying that which of these explanation maps give you a better explanation of the input image that you have. And based on their votes, you can kind of normalize the scores and try to see which explanation method is the best. Yeah, which of these, which of the explanation maps give you the best results. If that makes sense.
Yeah, makes sense. So if you have a data set which is especially general, like we have a bounding box data set, then after getting the classification maps, how do you go about comparing them? Do we approximate the bounding box across the map that we get, and then we compare both the bounding boxes?
No, the thing is that you can try to find out how much highlighted portion is there within that particular image. I mean, within that particular bounding box for one image. And in another image also, you can try to do the same, and you can quantitatively compare both of them, if that makes sense.
Yeah.
Do you understand what I mean?
Yeah. All right. I think that's all. We don't have any further questions. Thank you everyone for joining. It was a wonderful discussion with you. Hope to have most of the discussions on differential privacy and federated learning in the future. Thanks again for joining.
Thank you, Sahib, for organizing this.
Thank you, Sahib.
Thank you.